Swayam Prabha. Digital India. Educated India.
So now, to give you one quick example, or the kind of force that is being exerted, if you analyze, let us say we have this vehicle tires, and in the vehicle tires, if you see the pressure that we are putting, you usually put a pressure of 32 or 33 something, which you might hear when you are actually putting the pressure. So different tires you put different pressures, which is varying around 32, 33. So what is that? So this 32, 33 is nothing but your units in PSI. So it is going to be, let us say, 32 PSI. So this 32 PSI is another unit, not Newton per square meter. It is pound per square inch. So this is FPS units. So pound per square inch. And if you convert that to Newton per square meter, that will be equals to approximately 220 kPa. So 32 PSI is equals to 220 kilopascal. So now this 220 kilopascal is basically the gauge pressure, because we are putting the pressure or measuring the pressure with reference to atmospheric pressure, and we know the atmospheric pressure is 101 kilopascal, and now we have gauge pressure of 220 kilopascal. Okay, now if I want to find out what is the absolute pressure that is within the tire, then I can add both of these, 220 plus 101, so plus 101, that will give me 321, which is nothing but my absolute pressure. Okay, so now you have understood the units and scales of pressure. Now let us understand how these are measured. These pressures are measured in various ways, but the pressure intensity P at a point can be expressed in terms of an equivalent column of fluid. So I can tell that, okay, pressure is this much. Let us say I'll tell pressure at this point is X. So this is in Newton per square meter. Or I can tell that the pressure on my head is 1 meter of water. So it is equivalent that 1 square meter of water column is standing for a height of 1 meter on my head. So that is the kind of pressure exerted on me. So, or if a person is submerged within water and it is the person is below 1 meter of the water surface, then the water head is 1 meter. And instead of telling that pressure is this much in Newton per square meter, I can tell in terms of head. So that is calculated by taking P by gamma. So gamma is nothing but your unit weight of the liquid or fluid. So P by gamma is going to give you that head. And please remember, when you mention head, it is necessary you always specify head in terms of what, because P is the pressure. Pressure can be just given in Newton per square meter. But the moment you specify in terms of head, it has to be head of water or head of air or head of mercury. It depends how you have taken the value of gamma. Gamma is the unit weight. So unit weight of the liquid you have used is going to give you the head in terms of that liquid. So it is necessary you mention head of what liquid. Let us now come to the instruments or measuring equipments. So first one is piezometer. Okay. What is piezometer? It is a simple tube. It's a transparent tube in which the liquid can freely rise. So I have some kind of pipe or container or chamber where there is a fluid and there is some pressure. Now I will make arrangement to insert a tube inside that chamber or pipe, so that due to the pressure the fluid is going to rise. And how much it will rise? It will rise to the level that the pressure and this water column exerting the pressure, both are balanced. Let us say I have this pipe, and in this pipe I have the pressure at the center. Pressure is, let us say, P, and now this P has to be balanced by the amount of liquid that is going to stand on top of this. Then only they will come to a rest. Otherwise, there will be some movement, and possibly this fluid is going to keep on rising till achieving that point. So, assuming that now the total water level or the fluid level has already risen up to this, now we can find out with the scale of this tube what is the head or what is the distance from the center of the pipe. Now, if I measure this distance, which is from this point to the point at this surface, I can take that as h. Okay. So, what is this h? This h is nothing but P by gamma or rho g. So, the unit weight of the fluid is rho g. So, P by rho g is h. Now, if I can measure the value of h, I can calculate the value of P by multiplying with gamma. So, this is nothing but your piezometer. This is always measured with reference to the center. Now, if you are connecting this device or piezometer at this point, then you are going to measure the distance, this, which is possibly you will have a scale from this point to this point, and you have to add this radius of the pipe to get to the center, so that you can find out the pressure at the center of the pipe. Otherwise, you are measuring the pressure at this point. Similarly, you can connect your piezometer at different locations, and finally you can obtain the h. But wherever you connect, the water is going to rise up to that level, because we know that the pressure due to this is going to vary within this also. Now, usually these piezometers are of transparent tubes, are of diameter 3 mm, which is very, very small. If it is too large, then it will lead to errors, and if it is very small like this, then it's measured. And if the pressure is very large, what will happen? Let us say I have this pressure, and the pressure is going to be increased within the pipe. What will happen? This level is going to rise, and at some point it will overflow. So, you may not really visibly put a tube which is very, very long, which is practically not possible, and you cannot always use piezometer for all types of pressure measurements or all magnitudes of pressure measurements. So, you have to have some other device. Let us look at those devices. This is called U-tube manometer. So, when you cannot really use piezometer, or your pressure is so high that you cannot have such a long tube, then you resort to this U-tube manometers. And in case of U-tube manometers, you can see that it has a form of U, and you have two different fluids, fluid A and fluid B. This fluid B is your manometric fluid, and fluid A is the fluid or working fluid that is actually in your pipe or that you are using, or that pressure you want to measure within certain fluid, that is your working fluid. And the fluid that is used in the manometer is called manometric fluid. So, U-tube manometers are devices in which columns of suitable liquid are used to measure the difference in pressure between 2 points, or between a certain point and the atmosphere. So, let us say you have a pipe. Within the pipe, what is the pressure you want to measure with respect to atmosphere? That can be measured. Or you have two different pipes where the flow is taking place, and you want to measure the pressure difference. That also is possible. So, the right side column of this U-dim is kept open here to atmosphere. That can be connected to the other pipe, and you can measure the pressure difference between the two. So, basically it is measuring the pressure difference between two different references or points. So, now let us see how it works. As I said, here you are using suitable liquid. So, what do you mean by suitable liquid? So, this liquid has to be such that it doesn't really overflow on the other side, or it doesn't go to the other pipe or other medium. So if this liquid is heavy, that means if the liquid has higher specific weight, then this liquid cannot really displace that to that extent what it could have displaced a lower or lighter liquid. So we have to choose the liquid in that way. Anyway, we will see that in more details. But now let us look at how this is measuring. So we already know that from our initial understanding that pressure within a fluid, within a continuum fluid at the same elevation is going to be 0. Now here if you look at this manometric fluid is extending up to this. So the fluid is continuous up to this. From this point of atmosphere, it is continuous up to the point that is PQ line, but then it becomes discontinuous. This is another fluid. So now we know that the pressure at this point along this line PQ, okay, so you have a point here, you have a point here at this interface. So the pressure at these 2 points are going to be same. That satisfies our basic fundamental principle. So now if we know that the pressure is going to be same at these 2 points, then we can equate the pressure at this location, let us say 1 or P, and pressure at Q. So what is the pressure at this location at this point? So that is the pressure starting from here. If we keep on adding all the pressures up to this, I will get the pressure. So let us say at this point the pressure acting as P1. So P1 plus I have some other pressure which is acting due to the standing column of fluid A. The fluid A is exerting the pressure due to its own weight. So that is rho A G multiplied by this column, and the distance of this column is nothing but x plus y. So this x plus y multiplied by rho A G is the unit weight of this liquid A or fluid A is going to give me the pressure. So that is the pressure at P. Now what is the pressure at this point Q? So that is nothing but your atmospheric pressure here, P atmosphere, plus due to the weight of this liquid. What is that? That is rho B, which is density of the liquid or fluid B, multiplied by G multiplied by X, the distance. Okay. So this expression we could write by equating the pressures along this line. Okay. So now if we resolve this, we can write down P1 minus P atmosphere is equals to rho B minus rho A Gx minus rho A Gy. Anyway, this is not difficult, so you can always write and resolve. Now the point needs to be understood is, initially this liquid, when it was not connected to this, so obviously this would have been open, the left limb would have been open, so you would have again P atmosphere on this side. So if you have both sides connected to atmosphere in the beginning, or there is no pressure or zero gauge pressure exerted here, then both of these will be at this level. So this limb will be at this level. Now because of this additional pressure, this is being pushed and this has risen on the right limb and it has been lowered on the left limb. So that's why you are getting this differential elevation, and if you take this and calculate, you can get the difference in P1 minus P atmosphere, which is nothing but your gauge pressure at the location P1. Okay. Similarly, if let us say the pressure at P1 is less than the atmosphere, then what will happen? This atmospheric pressure is going to be lower, or it will push this right limb and the liquid will be lifted up on the left limb. So anyway, we may not know that. Our purpose is to measure what is the pressure inside this. So if I connect the U-tube manometer, I find that I get some profile like this, and where I get the x value here, or it is rising by an amount of x. So I can similarly I can equate both the pressures at line PQ, because this is the level of fluid in the continuous fluid where pressures can be same. So I know the difference between these two locations, that is P and this location interface. So I can write down that P1 plus rho A G multiplied by Y plus rho B into G multiplied by X. So that is the pressure here, is equals to P atmosphere. So now if I equate this, I'll get this P atmosphere, because P atmosphere is higher, the equation is written like this: P atmosphere minus P1 is equals to G multiplied by rho A Y plus rho B X. Well, now if you write P1 minus P atmosphere, you will get a negative value, and you will call it as negative gauge pressure or vacuum pressure. So if you know already that you are calculating vacuum pressure, you can also write down P atmosphere minus P1, where it will give you a positive pressure, positive value, and that is nothing but your vacuum pressure. So this is how the U-tube manometer operates. So there are other types of manometers. We call it differential manometer. So usually in a single pipe, let us say I want to find out the difference in pressure at 2 points, and as the flow is taking place through this pipe, there could be losses, there could be some change in the pressure from one point to the next point. So I want to find out. In this case also, we can connect the U-tube manometer like this, and it will show us the difference in pressure with this difference in the level of manometric fluid. So we can measure that what is the difference in this level, that is from this point PQ to this line. So X is that difference, and by taking that, we can find out what is the value or what is the pressure difference. So the pressure difference P1 minus P2, if you want to find out, first we can find out the pressure at this location and at this location. Let us say it's P and Q, and if I start balancing these both, the P1 is the pressure at this point, plus rho W G multiplied by X plus Y. So X is this difference, plus Y is up to the center of the pipe. So this fluid column is added here, or the weight of the fluid column is added, is equals to P2, that is the pressure at this point, plus rho W G Y. Rho W is nothing but the unit or density of water here. W is referring to the water or working fluid. Sorry, not necessarily water, it's working fluid. So rho W multiplied by Gy, that is up to this point, and then from here to this you have the manometric fluid, that is rho M multiplied by G into X. So now if you substitute this, you will be able to derive that P1 minus P2 is equals to rho M minus rho W multiplied by Gx. Okay. So now you see that this is only a function of X. There is no Y in this, because they both have been cancelled out on both sides. So if you can use a differential manometer, and you can measure the distance between these two, the difference between the two limbs in the manometric fluid, that you find out as X. This X is going to be your value using which you can find out what is the difference in pressure. And usually you know already what is the density of manometric fluid, you know the density of working fluid, and gravitational acceleration is known, so you can easily find out the pressure difference. Sometimes this pressure difference is also represented in terms of head difference. So to find out the head, we know that you have to divide with the unit weight of the liquid. So here we want to find out the head difference of the working fluid. You want to find out the head difference within this point or in this fluid flow. So that is nothing but your working fluid. So if you take the working fluid, that is divided by rho W G, then you will be able to get this expression H1 minus H2 is equals to P1 minus P2 divided by rho Wg is equals to rho M by rho W minus 1 multiplied by X. Okay. So these simple expressions are very, very useful for finding out the pressure difference between 2 points in a flowing fluid within a pipe. So you will be using this expression in your laboratory experiments quite number of times, and then you will be able to understand the applications. There are other different types of manometers. One is inverted tube manometer. In the case of inverted tube manometer, if your fluid that you are having here is of higher density and you have the manometric fluid which is of lower density, then it is basically uh, uh, kept in the inverted manner, and in that case what will happen, this lower fluid is not going to enter to this lower density fluid is not going to enter this fluid, so that it will not damage or the total system is not going to be affected. So this inverted tube manometers you will use when the manometric fluid is less than the working fluid. And if you write down the expression in the same way, you will get this expression, which is P1 minus P2 is equals to rho W minus rho M into Gx. So x is nothing but again the difference in the manometric fluid. Okay. There is another type of manometer which is inclined tube manometer. Why this inclined tube manometer is used? Sometimes if you put this manometer, you will find this difference x that you are getting here is very, very small. It may be very difficult to read the meniscus and identify what is the x value. So to get that, we can amplify the value. So what we can do, we will have the scales here, and by taking this inclined tube, the same x is going to be elongated over a distance s. So that will depend on the value of theta. So if theta is small, then considerable magnification of the movement of the meniscus can be achieved, and once you have that, then you can read this value of s, and once you read the value of s, then you can convert that to the value of x. Okay, you need to convert that to the value of x because that is the fluid head standing on that surface, not this s. Okay, so you can use the inclined tube manometers to measure very small variation in pressures. Similarly, to measure very small pressure differences with maybe more precision, there are instruments called differential micromanometer. So if you look at differential micromanometers, you can see that differential micromanometers, you have two different types of chambers, and this is U-tube manometer. You see, this is the pipe diameter which is connected to the pipe or to the working fluid system, and you have manometer that is here, and this has one chamber which has a cross-sectional area of capital A, and you have another one which is a cross-sectional area of small a, so which is of lower diameter or lower cross-section. Now we have three different fluids here. One is working fluid, one is, let us say, the gauge fluid of density rho g, and another one is manometric fluid of density rho m. Okay, so three different fluids, and initially this gauge fluid is at this level and manometric fluid is at this level. Now the moment you connect that to the pipe, which is, let us say, like this, okay, and there is a flow within that, and if you connect it to that, then because of the pressure at this point and this point, there will be variation. So assuming that the P1 here is greater than P2 here, then you will have higher pressure which is going to push this liquid down, and you will have a lower pressure, and this push is going to result on the other side, and there will be a change or difference in this manometric fluid. So what will happen in this chamber which is larger, there will be some push. Let us say this push is nothing but your delta z. Okay, and this delta z is also going to reflect on the other side, but the small amount of volume that has been displaced here is going to displace quite a large amount of volume in this smaller diameter limb, and that difference is going to come here, and that you have here as y1 y, which is going to result in this difference. Total is y, and if I take the mean position of that, there can be y by 2 and y by 2 on both sides. Now, if I take and calculate the pressure on both sides, then I will be able to balance it at this point, which is PQ. If you see, this is the line where fluid is continuous and I can have 2 points on this both sides, and I will again same way calculate what is the pressure at P and what is the pressure at Q and equate them to find out how this works. Okay. So in this case, in general, manometric fluid is heavier than the gauge fluid and gauge fluid is heavier than the working fluid. Okay. So if we start writing the left column, the pressure at P, then it is going to be P1 plus the working fluid head, which is here, which is, let us say initially it is H, plus there is a delta Z which has been displaced due to this pressure. So H plus delta Z multiplied by rho Wg plus rho G is the gauge fluid. So that is equals to Z, which is the distance. Z is nothing but your value that you had in the beginning, which is possibly measured the value of Z. Yeah, so it is not shown, but Z is measured from these two, sorry, from this point. Yeah, this is Z. This value is Z. So Z is measured from here. Yeah. So Z is measured from this point, which is the initial position of your manometric liquid and the initial position of your gauge liquid or gauge fluid. So these two Z, this value of Z minus delta Z, because your Z, there is a displacement here, so minus delta Z plus y by 2, because this difference has come now, which is nothing but y by 2 from this mean position. So this will give you the weight of this gauge fluid. Then that is equals to P2 on the other side plus rho Wg H minus delta Z, because it has reduced now, plus rho G, that is the gauge fluid, multiplied by gravitational acceleration G multiplied by Z plus delta Z, because the delta Z has increased here, minus y by 2, which has reduced here, plus then you have manometric fluid. So manometric fluid is rho m G y. So if you equate both of this, and then you can substitute this expression, that is A delta Z. So here if you see this area of this bigger cross-sectional area of this tank is capital A multiplied by delta Z, that is the difference here. This fluid is accommodated in this section. So this A delta Z is equals to small a cross-sectional area of this tube multiplied by y by 2. So this difference is accommodated in this port, in this part of this column. So if we equate, now we substitute both of these, we can rewrite this expression P1 minus P2 will be equals to Gy multiplied by rho m minus rho G 1 minus A by A minus rho W A by A. So this is basically a function of the manometric fluid, gauge fluid, and the cross-sectional area of the manometric, the smaller diameter limb, and cross-sectional area of the larger diameter limb. So these parameters are all known to us. What we need to only find out is the value of y, and that we can find out by reading this difference. So we don't need to read all this delta Z and so on. We can just put this manometer and find out the value of y, that is here, and then substitute in this expression to find out the difference in pressure between two points. Okay. So this is the working principle of differential manometer. So I think with this we'll stop. There are other pressure sensors which are also available. This is pressure transducers, where you will have a diaphragm here, and this diaphragm will be deflected due to the pressure acting on that, and that deflection is measured electronically and it is transferred, and you can find out there are different ways of measuring pressures nowadays. there are a lot of pressure sensors which are used to measure very high pressures at what depths of, let us say, 3000 meter, 4000 meter under the sea, and these are implemented for measuring the differential pressures during a tsunami or any extreme events in the sea. So the tsunami buoy system is usually using such kind of pressure measuring systems. All right. So I think with this we'll stop here.